So I guess we can get started. Is the audio okay here? Everybody nods, everybody okay? You're happy with the audio? All right. So a few years ago, I got sucked into this conference after probably spending way too many days at an AI conference with all these young kids. And they keep telling me that 90% accuracy would be fantastic. And they explained the scale to me. And I said, if United Airlines, if all the American airlines would be at 90% accuracy, we would be out of planes within a week. And I said, 90% isn't good. And then I ended up giving a presentation here among white-haired people, and they told me storage needs attention. 1 bit missing, data can be corrupted. So I'm glad I'm back here at this one where it's a bit more sensical than some of the other areas which we deal. About a year ago, no, actually last year, we gave a presentation on a new transport layer protocol. It's not that new, it's a few years old. John Ousterhout started it, and this is basically an update session. So for those of you who haven't seen last year's talk, feel free, it's probably still available online. For those of you who want a quick one, I have some slides going into the key details from John Ousterhout's presentation. So what we're going to talk about is the protocol itself from John. And one of the big questions we got, in particular from storage networking guys, was, well, can your Homa protocol coexist peacefully with TCP? I mean, like, is Homa going to mess up my network, which typically runs TCP and or RDMA or things like that? So we took this as an action request. And the other action request we took from John, who basically said, you should not be running any of those protocols entirely on a CPU and software anymore, right? For the world reaching 100 gigabits, 200 gigabit links, the world is talking about terabit links these days. Leave it out of the CPU, put it in some form of acceleration. And because we're FPGA acceleration people, we started to put something into FPGAs. And because Homa, the name, has a couple of trademarks in the electronic business, I'm not too concerned about this one bilge pump manufacturer who calls this product Homa. We decided to call it Quad RP, as in Reliable, Rapid, Request Response Protocol. If you find some better abbreviation, we're not stuck with the name yet, but that's basically how we distinguish between Homa, the invention from Stanford, on anything that goes into implementations. And the last one is actually a call for collaboration. Oh, hi, Tom. A call for collaboration, because this is not really a product of us or something. We think that this needs an initiative by industry, by smart thinkers, by academia, to get the ball rolling on better protocols, more suitable for storage networks, more suitable for HPC clusters, and similar tasks. My presentation today is a little bit of my work, basically putting the data together in slide form, but the real work is John Ousterhout. Quite frankly, he's a pleasure to work with. My colleagues from Missing Link Electronics, mostly in Berlin and in New Ulm, Germany, as well as the University Institute I'm kind of co-located with, where we had a couple of students. Bjorn is one of them. I even put an umlaut in there for him. That tells you how good a work he did, who basically started to put certain concepts into FPGAs. And about 7, maybe 8 years ago, when we saw a fabric war, remember this? Like CAPI and Gen Z. Well, starting to see a little bit of a new wave of transport layer protocols, right? We see Homa on the left-hand side. I'm going to dive into this one. We see Tesla's protocol, and this is not for in-vehicle networking. This is for their Dojo supercomputer. Right? They announced it on Hot Chips about a month ago, and they call it Tesla Transport Protocol over Ethernet. Okay? Not diving into too many details. And obviously, the Ultra Ethernet Consortium is working on this with a clear message for all three of them. to tame tail-end latencies. Okay, and again, so my presentation today is also a call for collaboration. If you have some ideas, some goods or some bads, right, let us know. So let's look at the Homa protocol. Just two of the key presentations, papers that John gave about his technology. The first paper was actually written in 2019. It's time to replace TCP in the data center. Obviously, that's a bit provocative. We probably need something that complements TCP in the data center because we're not getting rid of it. I'm a software engineer by training. I know how hard it is to replace very well implemented, well-known APIs like the TCP socket interface. The second one is a bit more recent, which is when John took a break and implemented the Homa protocol as a Linux kernel module. Okay, and it's open source by now, and it has some strengths, some weaknesses. We're going to talk about some of those. And that Homa module, as we call it, was for us kind of a golden reference to do all the experiments with. So I'm kind of a top-down person here, so let's look at why Homa might be interesting and why we started to look more closely into Homa. The first thing is the experimental results that John published in his various papers. 100% to the last digit, we were able to reproduce them. That's not always the case with all the academic work that we sometimes suck in and figure out whether this is useful and applicable for some of the work that we're doing. So that's the first message. The second message is all John's current experiments were run on a 25 gigabit Ethernet network. And we all understand the moment we scale up higher link rates, the computational burden of a software protocol will be even higher, okay? As it's in either TCP over IP version 4 or whether it's Homa over IP version 4. So let's look at this chart and let's dissect it because it took me a while as well to figure out what this chart says. So on the x-axis at the bottom, you see a distribution of packet or message sizes. And John's speak, he calls a message an atomic piece of information that needs to be transported. That could be a page of phone numbers. Okay, it's a unitary thing, it's an atomic thing, and that eventually gets broken up into PDUs or packets, and the message size is basically the granularity of sending information. And what you also see, it's like in a 20, 40, 60, 80, 100%. What you see is 20% of the messages are 367 bytes or smaller. 100% of the messages are 1 megabyte or smaller, okay? So obviously, we have something with message sizes. Then on the y-axis, we see what John calls a slowdown. The way he measures the slowdown, that's an experimental number, is by computing the round trip time on an unloaded network, okay? And then the round trip time on a loaded network. And the round trip time loaded divided by the round trip time unloaded is what he calls a slowdown, okay? So green TCP P99, I don't need to explain this. P50, let's ignore this because this is a bit of a talk about tail-end latencies, taming tail-end latency. So if you start with TCP unloaded versus TCP loaded, you have about 100 to 200x slowdown. Okay, has a lot to do with TCP's congestion control mechanism, fair bandwidth sharing, as well as how the Linux kernel, the pacer, handles TCP. The blue bar is, the solid blue bar is Homa protocol at P99, which is less than 10. And just in light of full disclosure, the round trip time, the absolute numbers, are very, very similar. Actually, Homa is a little bit better than TCP. So it's not like, yeah, Homa starts off so badly, but the slowdown isn't that bad. So the absolute round-trip time numbers are similar, or for Homa, sometimes better. So obviously you pay, in this case, a 19x penalty for running TCP on a loaded network. And load, that's basically 20 gigabits per second. That's the load of the network. That's on the top one. John took a couple of workloads from academia and from some of his research partners and augmented that. And the difference in workloads is mostly the difference in message sizes. All right, so he has a couple of workloads which have a lot of little messages. Then he has a mixture like this one, and he has a couple of workloads where he has a ton of large messages. Okay, so when we saw that slide and when John explained the slide to us, we got interesting because we do a lot of real-time, high-performance, real-time networking for all kinds of facets, and we figured, wow, that's a lot. Okay, that's an order of magnitude. We're interested, so we're engaged with John. Oh yeah. That was the real numbers we see, where we see, okay, if you do the green bar in a loaded network, it's more like 2 milliseconds round trip time. And if you look at the blue bar, it's more like 100 microseconds, okay? And last week, I went to the AI Hardware Summit in San Jose, and one of the key nightmares was the energy that we burn through GPUs, literally sitting idle, okay? I'm amazed they pay people to buy GPUs who sit like at about 15 to 25% idle, while us engineers, if we spend half a day doodling around on something, we get a hard time. Okay, so obviously between 2 milliseconds in order to close a job or 100 microseconds, there's a huge difference, and that has an immediate implication on HPC workloads and or AI cluster workloads, in particular for training, not so much on inference. So the first thing that I want to basically explain is Homa is message-based. TCP is stream-based. You open up a connection and then you stream data from left to right. Okay, Homa is message-based. And the key thing is this allows you to do very efficient load balancing, mostly on the CPU side, because you don't really need single sockets and all this mumbo jumbo there. You send a message as an atomic element. It obviously gets segmented into network segments, and that message is received. And the real fun part behind this one, it allows you to do a scheduling on the receiving side as well as on the sending side, which encourages run-to-completion jobs, SRPT. The second thing is there is no connection in Homa. I mean, like there's a subtle thing like that, but once a message has been transported, in TCP, you may tear down the connection, right? Or not, because the burden of it is high. But in Homa, you're done, okay? That means you don't have to keep 2 kilobytes of state messages, state information around in software for all these many connections that you're opening up, okay? So if the lifetime of a message is done, the message is delivered, that lifetime is over. And the concept is really matching what we call RPC, remote procedure calls. Somebody requests some data, that data gets sent over, we call it request response, okay? And each RPC per se is then independent from each other. That means nobody needs to schedule these different RPC messages into one or multiple TCP IP streams, okay, and then deal with that. And then we have no head of line blocking per se as we stream things and then de-stream things. And the last thing is the connection setup is very low, right? So obviously there is something to send some data and the recipient needs to understand that, but that compared to the round-trip time penalty that we see with TCP or even with Tesla's protocol does not exist. And what Homa then does, it's a reliable protocol. So it takes care of the end-to-end RPC reliability, typically done by the application, but also taken care by Homa, understanding that pieces of the message are missing or got garbled. And the other thing is, which as we are touching base with more and more people who are willing to look at Homa, is Homa uses receiver-driven congestion control. TCP kind of is sender-based, right? You get the acknowledgements and eventually the sender throttles. In this case, the receiver determines how much data is basically sent, mostly in order to conquer the in-cast congestion problem. Now, we heard good and bad about receiver-driven congestion control. Some people are absolutely against it. Some people are absolutely for it. We understand that PCI Express with flow control to some degree is receiver-based congestion control. So we have protocols in practice which have very high bandwidth and use receiver-driven congestion control. And in order to get this done efficient, the Homa protocol does a little trick where it said the first number of messages, which are determined by what we call the bandwidth delay product, okay, get sent out unscheduled. Because it makes no sense to say, can I send you something when, well, I just sent you something, okay? The request is probably overhead, so just send me this stuff, okay? Kind of like senior engineers talk to their boss. So the sender sends data, and eventually the receiver says, okay, I got data, okay. And that's when the scheduling starts. And that's when the priorities kick in. And what John's experiments suggest is that this is really good to reduce the congestion in these top-of-rack switches. And it really is good to handle shorter messages in favor over longer messages, okay? And the message size now also allows the receiver, because the message size is part of the message, okay? Like, give me the phone book of New York. The response is, well, this is 8 megabytes, Hendrik. Do you really want it? No, give me chunks, okay? So as a receiver, I can predict the future. I know I need the phone book for New York. I need the phone book for London. I can juggle, okay? So I can do load balancing on the receiving side of things. The other thing that the Homa protocol uses or can use is it uses a priori understanding of the underlying network. So obviously this is not going to work in the internet, but in a data center where you have certain understanding of your workloads, you have certain understanding of your infrastructure, that's helpful. And what Homa then can use is priorities in most of these network switches. Where in particular, some of these smaller messages, shorter messages, get handed a higher priority, so they get transmitted first, okay? So we can continue on this run to completion idea. The other thing is, John did a couple of experiments and eventually found out there's still some slack in the network. So his approach was actually to do what he calls overcommitment to the network protocols. So you can do something like this, and it still makes the Homa transport very reliable, and in terms of tail and latency, very predictable. So again, to the slide, okay, so this is the result from John's paper, workload 4, 80% load, 25 gig Ethernet. You see the distribution of the message length, and this one also talks about data center TCP in the P90 9th percentile, okay? So that's when we got hooked, okay, and that's when last year, oh, and Homa has no order requirement. So you can do packet spraying, you can do out-of-order messages. All you really care is one message gets transported, the data in between gets then reassorted by the recipient. That means you don't have to resend N pieces because some portions got missing, okay? And that also allows us to do better load balancing on the CPU. Here's a couple more information. John gave this implementation for Homa module, which we call Homa module as the Linux software kind of golden reference C-code implementation. And this particular implementation uses, again, a priori knowledge, which is the link rate between the NIC and the top of rack switch, for example. You can set the NIC queue length for handling SRPT, basically the estimated time until the transmit buffer will be empty. Okay, so the Linux spacer can start pushing data into the NIC. What we also saw is that this has some goods and some bads in terms of coexistence and or interaction with other protocols Linux runs on, like TCP. But technically, it allows you to send data through the TCP, through the TX spacer in Linux, and then all the data gets spread out, handled by the Linux software. It can handle distances between machines in terms of a non-uniform RTT, like if you have hops in between or longer cables, if that matters, and obviously priority queues in this. And the other thing is, this is data in motion, so to say, right? John is adding to this literally on a weekly basis. And just last week, he told me, Enric, Stanford University gives me some kind of a sabbatical. I don't know how that works. And that means I can work full-time on Homa, okay? So one of the questions that we basically were asked is, how can Homa coexist with TCP? I mean, like, will my TCP traffic get bonkers in terms of adding a little bit of Homa? Will Homa go bonkers if there's TCP around it? Okay, so that's one of the things we did. And again, we continued using John Ousterhout's experimental system setup, where we have a hardware setup, 25 gigabit Ethernet NICs or networking and switches. The NICs is a combination of standard Intel NICs and or Mellanox ConnectX NICs, because they're kind of supporting the TCP buffering and scheduling. We use, quite frankly, a dead old computer for that, or dead old servers for that. And then we use the Homa module as it was published by John in December 23. He has a couple of test cases in there. He calls it CP versus TCP test, which is basically his protocol versus running TCP. That's how we compute the slowdown numbers. We run this one. And then we basically said, how do we add TCP traffic to the game? And we decided, let's have iPerf as it's reasonably controllable in terms of bandwidth, right? From any to any. And just add background noise in flavor of TCP streams. And then let's look at whether iPerf reports anything going different when there's Homa involved, and whether the Homa and the TCP slowdown numbers will change when we put massive iPerf traffic into the network, okay? And that's what we basically look at. We look at the round trip times and also at the slowdown times. Plus, again, we look at what happens to iPerf as an easy means for us to look at what happens to the TCP traffic. And again, we call that TCP traffic background noise. In your network, in your storage network, that will be the traffic you care about. Sorry for calling it background noise. And because we're pretty experimental guys, okay, we didn't run too much network simulation on them. We just built the cluster, used Cloud Lab for that, and we're starting to build one in-house. And we did a sweep. So at the top, you see like TCP stream target load in 10%, 30, 40, 50, 60, 70% of what the network provided. And then we use the Homa numbers, same as 10, 30, 40, 50, 60, 70%. In terms of creating the foreground traffic, and we ran it through the 4 workloads that really mattered, workload 2 to 3 to 4 to 5, and obviously some combinations aren't applicable because you can't have 70% of iPerf traffic and 50% of Homa versus TCP traffic. okay? That would not apply. And then basically we looked at, okay, what does this one direction mean? Well, it basically means, if we go horizontal here, it means how does the Homa message traffic behave under an increasing TCP background noise versus TCP messaging? Okay, that tells us, is Homa really better when there is a lot of TCP traffic going on? Right? Because John's charts only were 100% Homa or 100% TCP. And the other one was, how much does this TCP message-based traffic disturb the TCP stream traffic? Okay, we all have an understanding, yeah, TCP, fair bandwidth sharing, there will be something in the TCP congestion control. And quite frankly, how much does Homa do to the TCP stream traffic, right? And the way we did this, we got tons of these slowdown charts, and they all look like this. And I save you from looking at this, but so you get the gist, and we zoom in into some of those, right? So we got, this is for workload 4, we got one for workload 2, we got tons of things, and we stitched them together. And at one moment in time, somebody expected, I have a big screen, like an 8K screen. All I have is this little Chromebook, okay, in my phone. So monster data. We're absolutely willing to share that data with anybody who is interested, okay? We're not trying to hide things here, because quite frankly, if anybody takes this apart and we find out why this Homa protocol will never make any sense, the better for everybody involved, okay? No energy time, no engineering time wasted. So again, how does Homa behave under increasing TCP background noise? Okay, how does TCP deal with TCP's traffic, and how does Homa deal with this? Let's look at this. Okay, that's the first one. Just a little bit of Homa or TCP message traffic under a little bit, like 10% of TCP IPERF traffic, right? You can see the numbers here, 10 gigabits for Homa or TCP messages, and 2 gigabits for that, and 2 gigabits of this. And we see, okay, network not really loaded. Homa is a tad better, not significantly better, okay? The way we run these experiments, we run them many, many times, and we run them for 30 seconds. Okay, so the IPERF stabilizes, everything is stabilized, and then we run this. So that's why you can't see a flat line, but it's a little bit jagged here, but these are experimental data. So let's look at when there's a ton of IPERF traffic. Okay, you can see what John was talking about. Homa gets a little better when there's a lot of TCP traffic in the background, means the network is loaded. It's not as fantastic as we saw it, okay, because there's not really much Homa traffic going on, okay? Only 2 gigabits per second are going on as network traffic, while the background traffic is 14 gigabits, okay? The spike at the end is basically a measurement issue, because for some of the larger messages, something went wrong with a Homa module's pacer, and we're trying to debug that, okay? But okay, so looks like Homa is doing its job under heavy TCP traffic. Let's look at this data. Okay, yeah, that's kind of what we expect, right? A little bit of TCP background traffic, 4 gigabits out of the 25. And the key traffic is now Homa versus TCP, all right? So Homa performs as we expected, okay? Let's look at this again. So TCP slowdown was at about 9-ish, okay? TCP slowdown is about 30-ish. Okay, so we see an effect that TCP has on TCP messages, okay? 200-ish, okay? So hardly any traffic at all, slowdown very low for the green one. It's about, the slowdown is about 20-ish, okay? Now 200-ish, means TCP suffers a lot when there's a lot of TCP traffic. Let's look at Homa. Homa is about a slowdown of 10, 9 or 10, okay? Well, 30. Homa does not suffer that much under heavy TCP background traffic as TCP does. That's a key takeaway. Let's look at round trip times, okay? Where sometimes we care about absolute numbers. Scale is measured in microseconds, okay? So what we see here is, obviously because of packet size, we drew kind of a theoretical number, because round trip time for larger packets or larger messages, let me put it this way, larger messages will be longer because multiple transports. So here we see, okay, little traffic, okay, they're almost the same. Let's look at this. Things change, right? Everybody's round trip time got hurt, okay? So tiny little message, but what we see is Homa is better, okay? Consistently better. And here, it's kind of significant all of a sudden, right? Where the round trip time of Homa, when we have 14 gigabits of traffic versus 4 gigabits of background traffic, okay? Homa doesn't suffer that much in terms of absolute round-trip time numbers, okay? It's not only the slowdown which is better, but it's also the absolute round-trip time, where Homa can be much better. So that was our conclusion, and we said, okay, so from that moment on, if somebody says, how good is Homa when you run Homa on top of my existing TCP traffic, I would say, unlikely it breaks something, obviously depends on the workload. Unlikely it breaks something, okay? And unlikely that Homa suffers from you running TCP on your wire as well. And then we started to look at how can we accelerate Homa in terms of a hardware protocol. This is basically how Homa is implemented with the Homa module. So we didn't take the theoretical Homa protocol, but we took the exemplary implementation Homa module from John Ousterhout. And the way it works, it's integrated with Linux SNIA API. Okay, at this point of time, Homa has its own kind of pacer thread, which is a subtlety. John is aware of that. That needs to be fixed. Okay. And any data that is coming in then goes through what we call generic receive offloading, which isn't that good actually, okay? And then Homa does its mumbo jumbo, and any data that's been sent out, okay, basically goes through the Homa state and gets sent out to the NIC, all right? So that's kind of the software system behind. And then we basically said, okay, let's look at the two choices that we have. We accelerate a lot of software and a lot of protocols. And sometimes we pick offload engines, let the bulk in the CPU and just give it some, let's call it coprocessors. And sometimes we say it makes no sense that this piece runs in any shape of software at all. And we call it full acceleration, okay? And with a full accelerator, there's no software involved, no CPU, no cache misses, no nothing. It's basically registers, gates, which clock the data through and with very predictable latency. Other than a clock domain crossing, we count clocks until a packet has been processed, okay? The feedback we got is, well, you're hiding stuff in a chip. Could be my chip, but I'm nervous. I'm a software engineer. I need to see packets. Okay, I said, okay, understood. And then some of the other guys said, well, that's actually bad because I count packets, I count whatever statistics, so in court, I can warrant my service level agreement. I said, oh, shit. Yeah, we need something then in hardware too, okay, for service level agreements. But we basically said, which one do we start with? And the verdict was on the offload engines because too many people we talked to convince us, I want transparency. I want visibility into the internal guts of that protocol. Anything goes wrong, I don't want to have a big, whatever, key side VRV monster sitting there and digesting traffic, which the box doesn't even understand because it's not an official traffic, okay? It's not an official protocol yet. So be transparent, software. Let's start with the offloading approach. Okay, what we did is basically we took our FPGA NIC. It's open source. We've been working with these guys around UC San Diego for many years. Okay, it's a Corundum NIC. It has some strengths, it has some weaknesses, and basically took this as an infrastructure for adding Homa accelerators. And at the same time, this is a NIC which has reasonable offload engines anyhow for TCP IP, UDP IP, whatever, okay? Because it's a NIC. It's just implemented in an FPGA. And yes, we understand some deficiencies of the PCI Express subsystem, which adds a little latency to this, but every protocol is hurt by that. So it doesn't matter which protocol you run. So there are some inefficiencies of running a NIC and an FPGA using this implementation versus you got a monster optimized thing like an Intel NIC or Mellanox NIC or any of those. And then we looked at, okay, what offload engines do we have? Okay, the green stuff is state-of-the-art TCP. If you use one of those Mellanox Connectix card, you got checksum offload in hardware, you got receive-side scaling in hardware, okay, all nicely tuned with the Linux kernel. We're not talking about the Mellanox user space stack, which is a kernel bypass stack. We're talking about the Mellanox card with standard Linux TCP IP, okay? Large segmentation offload and large receive offload, okay? So if you send larger messages that you don't have to chop it up or aggregate it all in software, the NIC does that for you, okay? And we look at Homa module. Well, Homa module has very generic concepts, as we say, okay? And we said, okay, what do we do for what we call quad RP now, right? What metrics can we implement with reasonable work? We spent about half an engineering year in just making this work for the Homa module. And we said, okay, we want receive-side scaling just as it is run for TCP today, state of the art. We want large segmentation offload, just the state of art that we have in TCP in a modern Mellanox card, for example. And we want the same large receive offload. So we start comparing apples to apples. So we run different protocols, but both different protocols, TCP, Homa, use the same offload engines, okay? And we started implementing this, and this is kind of the first results, okay? So we all know how Homa acts versus TCP, and I'm trying to get my team to give me a chart with all three colors, okay? But this is a chart I got to. So under this metric, workload 4, 2 nodes, this is on a 10 gigabit network, all right? We see that the Homa module has a slowdown of factor 100. When you run offload engines, in particular for larger sized messages, obviously it goes faster, okay? The Linux kernel / the software has to crunch much less time in either receiving and or sending the data, and that's why we ballpark see a factor 4 point something, factor 5 in terms of improvement when you run just the same stuff that we do on a daily basis for TCP, run it on the Homa protocol, okay? We can translate this into slowdown numbers now for TCP, which was a 20x, 19x faster. We're now at 100x, okay? With just the same stuff that we do on a daily basis for TCP. I believe that's interesting because out of 10 milliseconds, we turn 100 microseconds, okay? That's why we're motivated to continue our work. And obviously, we believe the moment we run this at higher link speed, that's a 10 gigabit link speed, because that's what the hardware supported, results will get even better because the CPU will be more and more loaded and will more and more be the bottleneck. And this is kind of our forecast for full acceleration. We're looking at full acceleration for one simple reason. The Tesla guys believe in full acceleration. They say none of these protocols should run in software. Okay, kind of different from what we heard from other people, okay? But let's look at full acceleration. And we have a simple metric here, which is TCP, as in Linux stack, 4.19, a bit old, but it's a highly optimized Red Hat kernel, okay, versus a full accelerator, because we control the full accelerator for TCP, okay? And this is basically the round trip times, okay? In a full accelerator, the round trip times are basically 10 microseconds either way, depending on the software side of things. This is on a 10 gig NIC, okay? Nothing was optimized for that. Let's be frank here. It's just out of the box, two Red Hat boxes talking to each other, using netperf as a benchmarking tool, versus we run it in hardware. Okay, in hardware, we count clock cycles. Okay, we just published a simple white paper. We say, okay, that many clock cycles for us in order to transport data, TCP data through a hardware stack. Okay, and that motivates us, because if anybody is really focused on high bandwidth and reasonably predictable low latency, I believe we need to look into full acceleration for Homa protocol again. So that kind of concludes my talk. Here's my call for collaboration, okay? I'll be here all 3 days. Tom knows how to get a hold of me now, because he's been kind of a bit of our champion, okay? Or my parole officer. First one. We've asked for help to run stuff on a larger FPGA clusters, okay? ETH Zurich, we were told we need to contact them because at one point of time, AMD donated a bunch of FPGA cards to them. Anybody aware? We should talk to, we're interested, because we need an FPGA network cluster, and Amazon doesn't have that because the Amazon F1s don't give us access to the network, the FPGAs. Second thing is, other workloads. We understand that some of the AI workloads are fundamentally different, okay? And they need fundamentally different ways of modeling, okay? In order to understand what's going on. What we were told is, in particular training, has a huge burstiness. We don't have burstiness reflected in here, okay? The last thing is, help us look at other applications. Okay, we started to look at network storage systems with Tom's help. Last week, we engaged with a couple of guys like, help us run these AI clusters more efficiently. We're burning through a ton of energy, and we know these beasts are idle because some piece of data is not basically received in order to keep crunching. And the other thing, quite frankly, we're unopinionated. Unlike most engineers, we're unopinionated, okay? If there's something else we can borrow from, we'd be borrowing from. One of the ideas is, engage with you guys, shall we merge, to whatever it means, the concepts from Homa with concepts from Alta Ethernet and or Tesla's protocol, okay? Because they all try to do one thing, tame tail-end latencies. And that's all what we're here for as well. All right. Thank you so much. Any questions?
I may not know enough about network for the question to make sense, but how does Homa compare to Quick, which also seems to replace TCP?
Quick is an internet protocol. How does Homa compare to Quick? That was the question. So Homa is a LAN protocol. Quick is a WAN, as in wide area network, internet protocol. Homa is really optimized for networks which you control, like in a LAN setting. Quick, you can't assume anything because you could run through somebody's telecom router, which is halfway in between, okay? That's the fundamental difference. Homa is for latencies within, I would say, microsecond granularity. Quick is more for load balancing and spraying the internet as an unreliable transport. That's my understanding of these two different protocols. Any other questions?
Engagement from AI. I mean, it's the tail latencies, the throughput advantages are really good there. Who are you approaching in the AI community for this discussion?
So, who are we approaching in the AI community? So obviously the ones who are willing to listen to John and or us, okay. We had some first chats with Microsoft Azure, who is very open-minded and who basically explained to the world in many public presentations that the power consumption of GPUs is horrendous, and it's mostly because the GPUs are not highly utilized yet, okay? Same with Meta. Meta always had an open kind of source, open community collaboration approach. We're trying to get in front of Google. Who is most responsive today is the second tier cloud service providers, okay? Because their metric is, if you say, like, what is this facility? Oh, 2 megawatts, and it's 133. It's like, what's in there? We don't know. We just know the wattage. We own the land, we own the power supply, we own the building, we own the computers. We can tell you the wattage as an executive. I can't tell you 800, H100s, whatever. They don't even know the compute mix. The power seems to be interesting. They're aware of the low utilization, and they like the idea of doing something which has not yet been tried. Okay, because they've been in InfiniBand, they've been in Rocky version 2, and I said, oh, maybe it's time to try something new. Any other questions? All right. Cup of tea, cup of coffee, we can chat. Thank you so much.